Learn like a pro.
Okay, let's just jump right into this. You know, when most of us think about gravity, we tend to picture it as just this simple, invisible downward pull, right? The thing that keeps our feet literally glued to the floor. But today, we're going to completely shatter that basic definition. Welcome to this explainer, where we are going to look at gravity not just as a basic force, but as this highly structured, invisible architectural system that literally shapes the entire cosmos. We're going to examine the blueprint of how mass interacts with space, and finally, once and for all, separate the physical experience of your weight from the absolute nature of your mass.
To build this understanding, we're going to follow a four-part blueprint today. We'll start with the invisible gravity well, move on to defining the measurement, tackle the universal constant, and wrap things up with some really cool cosmic case studies.
So, let's kick things off. Act 1. The invisible world, looking at the gravity well.
I want you to picture this like a precision technical sketch on grid paper. Think of a planet, like Earth, as a mass core sitting right in the center of that 3D grid. Now, all objects with mass attract each other through this invisible, non-contact force. And they do this by generating these concentric circles radiating outward, what we call G-field orbits. If you think about this using a kind of dots and springs logic, as you move outward across those grid lines, away from the mass core, those invisible gravitational springs start to stretch out and loosen. And that loosening, that perfectly represents a weakening gravitational field the further away you travel from the anchor point.
Now, this illustrates a really fundamental, frankly kind of mind-bending truth. Literally all matter creates these fields. That pen sitting on your desk right now, it has its own gravitational field simply because it has mass. But because a pen's mass is so incredibly tiny, its gravitational force is completely negligible. We absolutely cannot feel it. It takes a massively huge core, like the densely packed layers of planet Earth, to generate a non-contact force strong enough to actually pull us toward its center.
So the really crucial point is how this field behaves right here, where we actually live. When we zoom in on the Earth's surface, deep inside this gravity well, we can see exactly how strong those invisible springs actually are. If you take a standard 1 kilogram block and hold it near the surface, the planet's field pulls down on it with a gravity vector of exactly 10 newtons of force. So every single kilogram of matter experiences that exact same 10 newton tug.
Moving right along to Act 2, the measurement, where we are defining G.
This brings us to a massively important concept in physics. We call it little g, or gravitational field strength. Formally speaking, G is the gravitational force per unit mass placed at a specific point in a field. Basically, it defines exactly how strong or weak the gravitational field is at that specific location. And we measure this in newtons per kilogram. We're essentially taking our blueprint from this grand cosmic scale and bringing it right down to the practical math of the ground we walk on.
Which leads us perfectly to the core equation for this explainer. W equals m times g. Weight equals mass multiplied by gravitational field strength. Just look at the structure of that for a second. This formula proves something huge. Your weight is not an inherent property of your body. It is just the physical consequence of your specific mass interacting with whatever specific gravitational field you happen to be standing in at the time. So, if your mass increases or the local gravity increases, your physical weight goes up.
I also want to quickly point out this really fascinating mathematical equivalence. We just established that Earth's field strength is 10 newtons per kilogram, right? Well, if you substitute the standard SI units using Newton's second law of motion, force equals mass times acceleration, the math perfectly reduces down to show that newtons per kilogram is the exact same thing as meters per second squared, which means Earth's gravitational field strength is literally identical to the acceleration of a free-falling object at 10 meters per second squared. Gravity times is a specific type of acceleration. How cool is that?
Now, to actively measure this downward pull, we use a spring balance, which perfectly brings that springs metaphor from earlier to life. Look at the internal mechanics on this. When you step on a scale, it is not actually measuring the quantity of matter inside of you. Your inherent mass stays completely constant. Instead, the internal spring of the balance is physically extending in direct proportion to the active downward gravitational pull, your weight. The scale is just measuring how hard the Earth is pulling on your matter.
All right, Act 3, the signature. Let's talk about the universal constant.
Let's take our measurement tools on a bit of a cosmic road trip. Compare these two environments. On Earth's surface, the 1 kilogram mass of an astronaut's boot weighs exactly 10 newtons. But if we take that exact same boot up to the moon's surface, it only weighs 1.6 newtons. Why? Well, the moon has a much smaller mass core, so its gravitational field is significantly weaker. It's kind of a fun way to think about it. Taking a lunar vacation is a fantastic way to instantly cut your weight down to a tiny fraction, all while your actual mass, the literal stuff you are made of, stays 100% identically intact.
So let's trace this journey all the way out, as that boot moves from the massive gravity well of Earth over to the weaker well of the Moon and finally out into the dark void of deep space. The physical experience of weight drops from massive to small to absolute zero. But look at how we represent the object's mass here. If you think of mass as simply a particle count, the number of particles inside that boot never shifts. Out in the absolute emptiness of deep space, you are completely weightless, but you still have the exact same mass as you did sitting right there in your living room.
Let's formally lock this in with a summary of the definitive distinctions between the two. Mass is the measurement of the quantity of matter in a body. It's your inherent signature, it is constant everywhere in the universe, and we measure it in kilograms. Weight, on the flip side, is simply the measurement of the gravitational force acting upon that matter. It's a highly localized experience that varies depending on the g of your environment, and it's actively measured using a spring balance in newtons.
And finally, Act 4, the application. Let's do a worked example.
For this last part, I'm going to put you right into the role of a cosmic architect. Here is a mystery scenario derived straight from our source blueprint. Imagine an astronaut takes an object with a known absolute mass of 62 kilograms to a totally unknown, uncharted planet. They hang it on a spring balance, and the scale reads a weight of exactly 279 newtons. So based purely on those two numbers, what is the gravitational field strength of this alien world?
Let's just walk through the vector math step by step. Step 1, we pull out our core architectural equation, W equals m times g. Step 2, we insert our known variables. We know the local weight is 279 newtons, and we know our universal constant, the mass, is 62 kilograms. So 279 equals 62 times g. Finally, step 3, we just divide the local weight by our mass to isolate g.
And there's the solution. 279 divided by 62 gives us 4.5 newtons per kilogram. Just by checking a scale and knowing our own mass, we've successfully deduced that this unknown planet's gravitational field is less than half the strength of Earth's pull. If you were to sketch this planet's gravity well in our 3D grid from earlier, the field lines would be spaced much further apart, roughly half as dense as the ones orbiting Earth. If there is one crucial takeaway you remember from our entire structural blueprint today, let it be this mantra. Weight is an experience. Mass is an absolute. Your mass is your universal signature, right? It's the unchangeable quantity of matter that makes you, you. But your weight, that is literally just the localized story of the specific gravitational field you happen to be standing in at this exact moment.
Which leaves us with one final, kind of provocative thought to look back on as we wrap up this explainer. If we know that weight is really just our temporary physical interaction with the planet's gravity well, how much energy would it actually take for an object to stretch those invisible gravitational springs to their absolute breaking point and escape the architecture of Earth entirely? What actually happens when you reach escape velocity? It's a fascinating question about the true limits of these invisible fields, and honestly, a perfect starting point for your next deep dive into the physics of the cosmos. Thanks so much for joining me on this explainer, and keep exploring.